everyone, it's time to start. First off, I want to talk about the homework that was due last night. I saw that the Lawn Kappa discussion board just blew up with questions, and I know a lot of people had trouble on that last page. Raise your hand if that was difficult for you, that last page. All right, the reason why it was difficult was because I combined questions from chapters 6, 7, 8, and 9. And that's hard. Usually the homework just focuses on the chapter that the lecture was just on. But that particular page, which was drawn from an old exam, covered material from 4 chapters that you had to basically integrate all that material. You didn't know where it was coming from. And I did that deliberately so that to prepare you for the exam. Because remember, a week from tomorrow is our next exam. Yeah. And we finished regression, and so what I did was I tried to integrate questions from all the chapters we've had on regression into that one problem as a wake-up call for you that you have to start studying now for exam 2. So that's why that question was really hard for you. So I don't think it's going to be hard for you after you review the material. And you expect to see questions like that, though, on exam 2. All right, so now we've finished regression, and what we're doing, we're going to talk about probability today, and the reason we're doing that is to prepare for inferential statistics. So far, all we've done is descriptive statistics. We have a bunch of data in front of us, a bunch of numbers, and we've summarized them with various statistics. The last thing we looked at was bivariate data, where we had 2 variables, and we summarized with the linear relation between the 2 variables with the correlation coefficient. All right, now what are we doing? Now we're moving into a whole different area of statistics called inferential statistics, which is where you don't have all the data in front of you. You don't have all the numbers about the whole population in front of you. You just have a sample, a random sample, and you're trying to make an inference about the whole population from the sample. So basically, we're going to be doing statistics on chance numbers. Think of it this way. Every time, for example, with a public opinion poll, in the last election, what was it, 130 million people voted? And the public opinion polls, the pre-election polls, were based on samples about the size of our class, about 1,000 people. And from that 1,000 people, we were trying to make inferences about how everybody was going to vote. So the idea is that every time you take a different sample, it's a random sample, you're going to get a different percentage of the people who wanted to vote for Obama, right? You're going to get a different percentage each time. So how do those samples vary? It's a chance procedure. And the same with when we look at, we started off with experimental design. If we randomly assign people to treatment and control at the end of the experiment, there's going to be some difference between the 2 groups. How do we know if that difference is due to chance? Is it big enough that we think it couldn't be due to chance, that the drug really worked, or the treatment group, the treatment really had an effect? Or is it small enough that it's just chance variations? We have to figure out a way to calculate chances. All of inferential statistics are based on probability models. So we're starting with simple probability today. And we're just going to spend, we don't need much. We're just going to spend 2 lectures on it. And some of it's stuff I'm sure you've probably already had. We'll start off real easy. So this is on page 109. And what's the chance of rolling a 5 with a fair die? So here's a die, in case you're not familiar with it, that has 6 sides. So what's the chance? Y'all know, right? I didn't get it. But at first, I should look at this definition of chance, right? How are we defining chance? And because we talk about chance all the time. Like the chance it's going to rain, the chance that we'll have a good football team or whatever, right? I mean, we do have a good football team, right? Right. The chance, all sorts of chances. We talk about it. The chance you'll fall in love with somebody in this class. Wouldn't that be cool? Then you can invite me to the wedding. Chances, we talk about chance constantly. But what are we talking? We have a very specific definition of chance that we are going to use now. And that is the chance of an outcome is the percentage of time one expects that outcome to happen when the process is repeated over and over and over again under the same conditions. Another way you can look at it is the chance of an outcome is the number of that outcome over the total number of possibilities. So for example, with a fair die, we have 6 possibilities, right? 6 possibilities. And what's the chance of getting a 5? It's 1 out of those 6, okay? And with a deck of cards, we have 52 possibilities. I brought a deck of cards in case you're not familiar, okay? And, sorry. And what's the, okay, so is everybody familiar with what cards look like? Maybe I better do this one on the PowerPoint, because people always say, well, I don't know what cards look like to me, so let's look at this. Okay, so what's the chance of, let's make it bigger. Okay, so here's what cards look like. There's 4 suits. These are clubs, diamonds, hearts, and spades. And each of the suits has 13 cards, running from ace to 3, all the way through 10. And then you have these picture cards. That's supposed to be a jack, a queen, and a king. All right, so what's the chance of drawing the queen of spades? Yeah, it's just going to be 1 out of the 52. You want to do this as an eye clicker? Might as well I just want to take attendance here. That's all I'm doing. So you know, just do this one as an eye clicker. It's a waste of time, isn't it, though? No? This is just a giveaway attendance. We'll see if anybody doesn't get it. I mean, it's circled. And it's bolded. But you know, I'm just curious if people click. We'll see what just happens just by chance if somebody clicks the wrong thing. That's what this will be about. So I'm going to stop it, okay? And we'll see. Yep, somebody did. Always. Just by the luck. You know, this is just what happens. Just by chance. Somebody here clicked the wrong thing. Okay. Well. All right. So, now let's go back to the document camera, okay? And fill that in. Okay, so it's 1 out of 52. All right. Now, what's the chance of drawing a queen? Out of 52 cards, how many of them are queens? 4. So it's 4 queens out of 52. All right, now what's the chance of rolling an even number with a fair die? What do you think? An even number. There's 6 possibilities, and how many of them are even? Half of them are even, half of them are odd. So I think everybody understands that. Okay, so now chances range from 0 to 1, or you could do it in percentages, and you could say they run from 0% to, yeah.
Are you not going to reduce it?
Oh, you can, actually that's a good question. Should I reduce it or not? I could reduce both of these to, I could reduce this to 1 out of 13 and this to 1/2. I think I'm not, because I want you to sort of, it's easier to see the logic of it this way. Of course, if you do reduce it, I'm not going to mark it wrong. But you can leave it like this. Might be easier for us to just leave it this way. Is that okay with everybody? And I'm not, of course, it's not going to be marked wrong if you reduce it. All right, So chances run from 0 to 1, or if you want to put in percent, 0% to 100%. So what, you know, but people always say, you know, people say, oh, 110% chance or 120%. That's just ridiculous. 100% chance means it's certain to happen, and a 0% chance means it's impossible to happen. And so you can't have anything outside that range. All right, now, here's what I say. The chance of an event occurring plus the chance of it not occurring has to equal 1 or 100%. Either an event occurs or it doesn't. And together they have to equal 100%. So sometimes, why I'm bringing this up is sometimes it's easier to figure, one of these might be much easier to figure out. So instead of approaching it directly, sometimes it's best to, let's say this one was really hard to figure out, the chance of it not occurring. Well, then you could figure out the chance of it occurring and then subtract that from 1. All right, here's an example. These are, okay, what's the chance of not rolling a 5 with a fair die? Well, the chance of, this one's easy to figure out either way, isn't it? What's the chance of it not rolling? Well, you could figure it out directly and say there's 5 ways to not roll the 5. There's the 1, the 2, the 3, the 4, and the 6, right? Or if it was harder to figure out, you could say, all right, it's 1 minus the chance of getting a 5. You know, you could think of it that way. Later on, we're going to see examples where it's very difficult to solve it directly. This one's easy to do either way. Do you understand? Any problems here? Okay, what's the chance of not drawing a queen? Well, this one's easy to figure out directly too. The chance of not, you'd think, okay, there's 52 cards. How many are not queens? How many are not queens? 48. But if you sort of were, or you could just say, okay, it's 1 minus the chance of getting a queen, which we've already figured out. It's the same thing. 1 minus 4 out of 52. It's basically the same. Here it's very easy. Later we're going to see examples where it's kind of hard. All right. So hold up. Whatever. Now, what is this concept of independence? 2 events being independent is really important in statistics. And what does independence mean? If 2 events are independent, it means that knowing one happened doesn't change the chance of the other happening. The chance of something happening is independent of whether the other thing happened or not. And they're dependent if the chance of the second event, of knowing one of the events, changes depending on what happened with the first event. All right, then they're called dependent. So a good example is with drawing from a deck of cards with and without replacement. Here's an example. Like, draw 2 cards without replacement is getting a heart on the first card, independent of getting a heart on the second card. So basically, the idea is this. Okay, what's the chance that you get you're drawing 2 cards. So you draw a card, and it's a heart. All right? Now, what's the chance that my next card's a heart? Well, if I put this back in the deck, the chance the second is a heart, given the first is a heart. All right? If I stick this back in the deck, and I shuffle them up and everything, what's my chance of getting a heart? It's the same as before. It's the same. It's what? It doesn't matter that I knew that was a heart. What's the chance that my second one's going to be a heart? Out of the 52 cards, yeah, or you could say out of the 52 cards, how many are hearts? 13 or 1/4. Okay, 13 hearts out of 50. All right, I'll see if I get a heart. It's only a 1/4 chance. No, I didn't. All right. But now you can think of it, all right, you have to compare that to what if the first card was not a heart? Okay, so here's the first card's not a heart. It doesn't make any difference because I'm sticking it back in the deck. This is with replacement. Oh my gosh. Oh my God, I can't believe it. Thank you. Yes. He should get up. I should sit down. I can't believe I did that. Was everybody confused on that? I was sticking it back in. This is with replacement. Whoa. Whoa, look at this. Let's start over and read the problem. It says without replacement. Without replacement. Let's do it again. Okay. So now we're doing it without replacement. I am so sorry. Now, what did I have? A heart on the first one? Pretend I just drew this heart. Okay, I got this heart. Now, the chance that the second is a heart. I'm not putting this back. So how many cards do I have left? How many cards do I have left? I'm not putting it back. How many cards? There were 52 now. How many are left? 51 cards left. Thank you. 51 cards left. And how many of those are hearts? 12. So there's 12 hearts. Now, all right, that's my chance. Let's see if I get it. Yeah. All right. Now, how about if I didn't draw a heart? I don't draw a heart. I don't draw a heart. I don't draw a heart. Okay, I did not draw a heart. All right. Now, 51 cards are still left. But how many hearts are left in here? I didn't draw a heart, so how many cards are left in here? How many hearts are left in here? 13 hearts. Are these the same? No, the chances changed. Are those chances equal? No, the chances changed. They changed depending on what? They changed depending on whether that first card was a heart or not. So those two events are dependent. They change depending on whether first card was a heart. Okay? As opposed to what I did the first time when I replaced it. Okay, so these two events are dependent. Okay? They're dependent. Now, obviously, I don't think we have to go through it again. If I put the card back in the deck, does it matter whether it's a heart or not? Does it matter? I'm trying to figure out the first card is a heart, and this. Does it matter? Just the chance of getting a heart. First of all, if I put the card back, I'm going to have 52 cards left. And the chance it's a heart doesn't matter, whatever I get on this. So it's a 13 hearts out of 52, whether I got a heart on the first one or whether I didn't. Because I'm sticking it back, my chance doesn't change at all. The idea is this. You have two events, the first card being a heart and the second card being a heart. It doesn't matter. If you stick the card back in, the deck has no memory of what was once taken out. It's not going to say, hey, you took that out, now I'm going to change it up on you. Once you put it back in, it doesn't matter. So are the chances equal? Yes. The two events are independent. That's the idea of it. So when you draw with replacement, the deck doesn't change. So the chances don't change. So the events are independent. It doesn't matter. It doesn't depend on what you got on that first card if you're sticking the card back in. And when you draw without replacement, it does depend on what that first card was. Does that make sense to everyone? All right. So that's the idea. Now, we have to think about let's look at this multiplication rule. The chance that two events both happen, equals what? The chance the first will happen times the chance the second happens, right? The chance that two things both happen. You're not going to add them together, you're going to multiply, right? The chance of first getting ahead, of getting two heads, let's say, when you flip a fair coin. Chance of getting ahead on the first is 1/2, right? And then half of those times you'll get another head. So it's a quarter that you'd get two heads. You wouldn't add a half and a half and say 100% of the time you'd flip a coin twice and get two heads. Obviously that wouldn't happen. So obviously that would be wrong. So you multiply, right? You multiply the chance that two events happen. You'd multiply the chance the first happens, and then of those times, what's the chance the second one happens? So you're multiplying. Now you have to be a little careful, because what if the second one depends on what happens with the first? So really the definition is that you multiply the chance of the first happens, you multiply the chance the first happens times the chance the second happens, given that the first had already happened. All right? That's what I say here. But when they're independent, it's really simple. When it's independent, you don't have to think about that, because it's just, it doesn't change. You'll see when I do these examples. Okay, so what's the chance of rolling a 5 and then rolling a 6? Well, they're independent, aren't they? If I roll a 5, let's say I rolled a 5, all right? That's a 1 out of 6. The probability of rolling a 5, it's going to be times the probability of rolling a 6. I don't have to worry about whether this changes depending on whether I rolled a 5 or not. Do I? Is it going to change? The probability of rolling a 5 is 1 out of 6. Now, because I rolled a 5, is that going to change my probability of now rolling a 6? Is the die going to say, hey, I gave you a 5, so, maybe I'm going to give you a 6. It's what, like, I'm not going to give you a 5 again or something. No, of course not. So it's 1/6 times 1/6. All right. Now, so when you're rolling a die, it's always going to be independent, because the die has no memory of what was rolled before. Whereas a deck of cards, it's not like it has a memory, but if you don't put the cards back, it's going to change up your chances. So what's the chance of drawing 2 cards from a deck with replacement and getting first a heart and then a club? So don't make the mistake that I just made on the other page. You got to read this really carefully, whether it's with replacement or without replacement. All right, now it's with replacement. So what are you going to do? What's the chance? Take it one by one. What's the chance of first getting a heart? We'll do the probability of getting a heart times the probability of getting a club. What does a club even look like? I can't even remember. Okay. That's a club, right? Okay. So so what's the probability of getting a heart? 13 out of 52 times, now, I got it. Is this going to change depending on whether I got a heart or not? No, because I'm sticking, it's with replacements, and it's not going to change. So I'll just say times what? 13 out of 52. Okay, we can just leave it like that. Now, and it's independent. As opposed to, what if I draw without replacement? Then what happens? The same problem. Okay, then I'll have the probability of a heart. That'll be the same, first getting a heart. But now it's going to be times the probability of getting this. Why am I having so much difficulty? That sort of looks like a person with big ears. Very strange. Okay. Okay, so I say times the probability of getting a club, given that a heart has been taken out of the deck. Given that a heart has been drawn. And now it's going to be what? It's going to be 13 out of 52, but what's the second one going to be? How many cards are left? 51. And how many clubs are left? 13. So this is slightly different. So this is, and these events are called dependent, okay, because it changes. This probability changes, given that a heart has been drawn. If a club had been drawn here, then I would have had what? 12 over 51. All right, any questions on that? So let's just continue with these. What's the chance of drawing 3 cards from a deck with replacement and getting no hearts? No hearts. What would that be? So you have 52 cards. How many cards are not hearts? 52 minus 13, which is what? 39. So you have 39. That's for the, take it one by one. That's the first card. And we're multiplying because we want that to happen. And we want no heart on the second. So it's 52 because we replaced. And it's still 39 times, what do you think? The same thing, because the chance isn't going to change, all right? But now, let's say we do, and is it, what do we call this? Independent or dependent? Independent, because the chances don't change depending on what the previous draw was. But now, let's do exactly the same thing, but this time do it without replacement. What do you think would happen then? They're going to be dependent, so you have to be careful. You start off, take it one by one. Draw the first card. Out of 52 cards, what's the chance of not getting a heart? What's the chance that it's not a heart? Isn't it going to be the same? Yeah. Now, how many cards do you have left? You assume this happened, right? Because you want them all to happen, so you didn't get a heart. Okay, so we did not get a heart. Now, we didn't get a heart. Now, how many cards are left? 51, because I'm not replacing it. And now, how many cards that aren't hearts are left? I mean, that aren't, yeah. We took out, yeah, 30 what? 38 are left that aren't hearts. And now I'll take, now the next one, let's say you assume that happened, you want them all to happen, so there's another one that's not. Okay, now we got how many cards left? 50. And how many aren't hearts? We're left with what? 39, 38. How many are not hearts? 37. Does everybody understand that? Does that make sense to people? They're dependent. Okay, let's try another one. Oh, this is going to be, how do you think we should, okay, what's the chance of drawing 3 cards from a deck with replacement and getting at least 1 heart? At least 1 heart. That means what? At least 1 heart means I could get 1 heart, or what? 2 hearts, or 3 hearts? That's going to be hard to figure out directly, isn't it? The chance of first getting 1 heart, because I could get 1 heart and the other 2 not being hearts. Or I could get, and that could happen in 3 possible ways. On the first card I could get 1 heart, or on the second card, or on the third heart, right? And then I could get 2 hearts, and that could happen in 3 possible ways. Or, because I could get the non-heart, then 2 hearts, the non-heart could be the second card, or the non-heart could be the third card. And then I could get, what's another thing that could happen? All 3 could be hearts. So I'd have to figure out the probability of getting all, oh, there's so many possibilities. Do you really want to figure out directly? So think back to that. If you can't, the probability of this event happening, at least 1 is hard to figure out. So we have this situation. Let's do it here. The probability of at least 1 heart. This is hard to figure out because it could happen in so many different ways. So this is hard to figure out. So remember, what would be the only other thing that could happen? Remember we talked about the probability of an event occurring plus the probability of it not occurring has to equal 1 or 100%. So maybe this would be easier to figure out if we could think about it not occurring. So what's the probability of at least one heart? It means, this is hard to figure out because it means you could get 1 heart, or 2 hearts, or 3 hearts. What's the only other thing that could happen? Say it, what is it? No hearts. The probability of getting no hearts. Doesn't that has to equal 1? Is there anything else that could happen? You're taking 3 cards out. You could either get 1 heart, you're taking 3 cards out, right? And it's with replacement. So you could either get, this time I got no hearts. That's one possibility. I could also get 1 heart, 2 hearts, or 3 hearts. Are there any other possibilities? I'm only taking 3 cards out. Is there anything else that could happen? Is there? Is there anything else that could happen? I'm taking 3 cards out. Either none of them are hearts, 1 of them's hearts, 2 or 3. So don't you think the probability of no hearts is easier to figure out? Did we already figure that out? Did we already do that one? Where is that one? The probability of no hearts, did we do that? Yeah, isn't it right here? So, we've got this right there. The probability of at least 1 heart plus the probability of no hearts has to equal 1. So, I should have left more space. So what should I do here? What's the probability of at least 1 heart then? 1 minus that, subtracted from both sides. Does that make sense? So the probability, so our answer is, for this, the probability of at least 1 heart is equal to, and it's just getting so crowded here, the probability of at least 1 heart is going to be equal to what? 1, I'm going to subtract that from both sides, so it will be equal to 1 minus the probability of no hearts, which is equal to 1 minus what? This, 39 over 52 times 39 over 52 times 39 over 52, right? Is that correct? So that's our answer right there. Any questions on that? So this is an example where if you're stumped and it's hard to figure out that directly, think of the only other possibility. All right, now let's try the same thing, but without replacement. Without replacement. You want to try that? We're going to do it without replacement. Okay, so we'll say the probability of at least 1 heart. Well, that's going to be hard to figure out directly, right? We're going to do the same exact thing. So we'll say the probability of at least 1 heart is going to equal 1 minus the probability of no hearts. 1 minus the probability of no hearts, which is equal to 1 minus the probability of no hearts. What would that be? We've already done it, haven't we? Right there. So isn't it right there? Right? Let's think about it again. No hearts. We had 52 cards, And on the first draw, there were 39 out of 52 were not hearts. But then it's without replacement. So now we only have 51 cards left, and only 38 of them are not hearts, etc. So it was this right here that's going to go in here. All right. Any questions on that? So basically, whenever you see at least one, that's hard to figure out directly. So I would instead think, okay, instead of at least one, think about the chance that at least one doesn't happen, which is none. At least one means 1, 2, 3, however many. The only thing that it's not encompassing, it's called its complement. Not really its opposite, but its complement. The two together, the probability of at least one plus the probability of none has to equal 100%. Okay, so now let's do the next one. What's the chance of drawing 3 cards from a deck with replacement and getting all hearts? First of all, it's with replacement, so we don't have to worry about probabilities changing. So, what's the chance of getting a heart out of the 52 cards? How many are hearts? 13. Can I just raise, you know it's going to be 13 times 13, you know, it's going to be 13 over 52 times 13 over 52 times 13 over 52. So can I just shorthand raise this to the 3rd power? Is that good? It's the same thing. Okay, now what's the chance of drawing 3 cards from a deck without replacement and getting all hearts? It's the same exact problem, but I'm not replacing things. You have to, so it starts off the same way. That's the chance of getting a heart on the first draw. But now what about on the second one? I can't just, it's going to change. Why don't you fill it in yourself? Make sure you know what's going on here. Okay, so first of all, you're not replacing, so the denominator is going to go down because you're not replacing the cards. Now, we're also getting a heart each time. So here, the numerator is going to change from 13 to what? 12 to 11. Okay, so I think you have that. All right, so now, these are pretty easy. Now, what's the chance of drawing 3 cards from a deck with replacement, and not getting all hearts? Not getting all hearts. That means there's so many possibilities. There's so many ways to not get all hearts. You could get all spades, you could get all clubs, you could get all diamonds, or you could get 1 heart. You could get 2 hearts. You just can't get all 3. You could get 0 hearts, like you could get all spades. You could get 1 heart. You could get 2 hearts. You just can't get all 3 hearts. So it's really hard to figure out directly. Let's think about it. If we wanted to figure it out directly, the probability of all hearts, of not all hearts, that's what I'm talking about. The probability of not all hearts. The probability of not all hearts. That's really hard to figure out because why? Not all means you could get 0 hearts, you could get 1 heart, you could get 2 hearts, just not all 3, right? Just not all 3, that's what it means. You get 0, 1, 2, just not all 3, just not all. So that's hard to figure out because there's so many different ways this can happen. So you want the probability of event plus the probability of it not happening equals 1. So you either get not all hearts, or what's the only other thing that could happen? You get all hearts. So the probability of all hearts has to equal 1. This is hard to figure out, not all. This is easy. This one is easy to figure out. We just did it. This one is hard. So what do you think we want to do here? We want to say the probability of not all hearts is going to be equal to what? This one is easy. Didn't we already figure this out? Where is it? Where is this one? Is it 10A? This we've already figured out. It's really easy. We just want to figure this out. So what should we do? It's going to be, what is it going to be? It's just subtract that from both sides. It's going to, the probability of not all hearts, it's exactly what we just did before. I'll write it again. The probability of not all is just going to be 1 minus the probability of all. The probability of not all, this is the hard one. That's the hard one. Probability of not all hearts is going to equal 1 minus the probability of all. Don't you see that? You don't even have to remember. You don't even have to memorize that. You can just say, okay, they have to add to 1. And which one is easy to figure out? This one. Plug it in and then just solve for that one. All right? Any questions on that? So it's going to be 1 minus that. 13 over 53 to the third power. Now what's this one going to be? This one goes with what? 13 over 53. I just added an extra card. Thank you. All right. What's the next one going to be, do you think? What's the answer to that one going to be? Probability of not all. It's going to be hard to figure out, right? So instead of figuring out directly, what are we going to do? I mean, we're just, okay, so the probability, it's the same thing. The probability of not all hearts. And it's hard. Plus the probability of all hearts. This one is easier. But the problem is, it's what? Without replacement. So what am I going to stick? I'd figure this one out. I mean, it's easy because you already did it. But let's say you hadn't already done it. You'd still say, okay, you either get all hearts or you don't. Those are the only two things that can happen. And this one, if you just try it, you're going to see it's going to be hard. So you say, okay, I'll figure this one out. And then you figure that one out. You'd figure that one out. And then you just subtract it from 1. So it's going to, the probability of not all hearts is going to equal 1 minus that. Does everybody see that? Okay, so it's 13 out of 52 times 12 out of 51 times 11 out of 50. All right, any questions on this? Do you want to like write this? Where should we write this? Just so you'll this might help you. Let's go back to this beginning where we talked about this and the chance of an event, this right here. And let's just like make sure to remember that these, because these were so easy that you could figure it out either way. So let's just write these down that aren't so easy. So let's turn back to page 109 and write the whatever you see, the probability of at least one of anything, at least one of anything. This is going to be hard to figure out because at least one means 1, 2, 3, 4, etc. There's lots of different ways. You know, it's hard because you could do, you know, depending on how many things you're talking about, it's 1, 2, 3, you know, it's a lot of different possibilities. So that's the probability of an event occurring, plus the probability of it not occurring. The only other thing, 1, 2, 3, etc., all the way, the only other thing is the probability of, this is going to be easy to figure out. It's complement, because it's going to be the probability of what? It's easy. What's the only other thing that, 0 is what we're leaving out here. It's going to be the probability of none. None, or 0, plus the probability of none has to equal 1 or 100%. All right? So this is the hard one. So if you see this, solve that. And you'll know as soon as you try to do it, it's going to be hard. Okay, so the same with the other one. What's another hard one? The probability of not all is also going to be difficult. This is also going to be hard because the probability of not all means what? Well, you could get none, 0. You could get 1, 2, 3, however many, just not all. Not all, however many things you're talking about. Not all 4, not all 5, not all 6, whatever. So that is hard. Plus, because there's so many different ways it can happen. Plus, what's the only other thing that can happen? Is that you get all. Like if it was all 4 of them or all 5 of them, you get all. So this is the easy one to figure out. So just figure that one out. And once you know that one, you know this one. Does this help? Okay, so just remember, as soon as you start it, you're going to know it's going to be hard. And you say, okay, let's just think of the only other thing that can happen. It's called its complement. All right, so we've got that down. Now, let's see what we want to do. Oh, boy. Let's see. What should I do? Oh, boy. I'm getting tired here. How about, let me see what kind of rapport I have with you guys. I want to see if I have ESP with you. Let me see. I just feel like I'm not connecting today. So I'm going to just see if you can like telepathically connect to me. Like I'm just going to I want you to just pick any card and I'll see if I know what it is. Do you think I can do that? I don't know. Oh. Should I pick out a person or just all of you? Let me think. Looking at you. Can't even shuffle properly. There's something. I'm not a morning person. Anyway, let's try it. Okay. I want to see if I have my usual thing with people. I have ESP. All right, let's try. Oh, boy. I'm rough here. Okay, you just tell me when you want to stop, where you want me to stop. Just tell me anywhere, and I'm going to, right there? Oh my gosh, okay. Oh, I don't even know this. Okay, I can't look, my eyes are closed, I'm not, all right. You told me to start right there. I guess it was this card right there. Okay, wait a minute, that's this way, right? Can you see this card, whatever it is? Okay, so I can stick it back. All right, now can I open my eyes? All right, I can open my eyes now. I want to see if I can know that card now. All right. Wait a minute. Don't tell me if that's it. I got to do something else. Hold on. I got to look at you and focus on you, not on the cards, right? There it came up again. It's telling me that might be it. Hold on. Don't tell me. It will ruin it for me if you just favor me. Okay. I think it's between those two. All right. I'm going to look at you. Look at that one. Look at that one. It's this one, right? No? Oh, thank goodness. Okay. All right, I'm back. All right. Oh. I feel better. I feel a connection. Okay. All right. Now, still can't shuffle, but I feel a connection. All right, good. Now, let's get back on target here. And a box has 3 red, 2 blue, and 1 yellow. Hey, before we even do this, let's try an eye clicker question. Let's try a real eye clicker question. All right, so let's go up here and let's see. What'd you say? I'm clueless. What? I feel like I'm like deaf, dumb, and blind up here, like sort of like I have to feel you through ESP, like I'm Helen Keller or something, and I want to touch you. I feel I can't hear you. I'm going deaf. I don't have my contacts in. I'm kind of blind, and I'm feeling like I'm just sort of feeling around through something to connect to you. Over there, where? What are you talking about? Help me out. I feel like I'm the stupidest person in this class. Like I'm just like trying to feel my way around. Are you trying to tell me something out there? And I'm not hearing you because I can't hear. I'm not seeing you because I can't see. And I don't want to touch you because that would probably be illegal. What do you want me to do? Somebody tell me what he's saying. I'm missing something. Can you tell me what it is? No? Oh, you're just fooling with me, I bet. All right. All right. Now, let's get back. All right. All right. Why can't I even do this? Okay, so now, and I want to get this out of here. All right, we'll start this. What is this? Oh, you're not even seeing it. Okay, or did you? What's the probability of drawing 6 tickets with replacement and getting at least 1 yellow? Try that one out. That's what we just did, at least 1. That's difficult. That's a hard problem. See if you can do it. At least 1. All right. Okay, so we'll stop it and see what you chose. All right, at least 1. Let's see what you chose here. This is the right answer, C. Very good. Most people got it. Great. Let's see if I can. This is. Why? Why is it that one? Because the probability of at least 1 is equal to 1 minus the probability of none. And do you see how that's none right there? Because there were 5 other cards. Do you see that? Does that make sense to you? So in other words, the probability of getting at least 1 yellow, you can get 1 yellow or 2 yellows or 3 yellows. That's really hard to figure out. You could get, in fact, you could get the first yellow on, in 3 different positions. The first, the second, or the third. There's 3 different positions here. You can get the non-yellow in 3 different ways. There's only one way to get the 3 yellows, but that's altogether 3 plus 3 plus 1. That's 7 different ways that can happen. So the easiest thing to do is to figure out the probability of none of them being yellow, any color but yellow, and there's 5 out of 6 times 5 out of 6 times 5 out of 6, and that's 1 minus 5, 6. Does that make sense to people? Okay, so let's go back to the document camera, and let's see what we want to do here. So we can quickly do these. These are sort of the same type of problem. Just to make sure that you've got it down, we can do these together. So you have a box that has what? 3 reds. So let's just say 3 reds. We don't know what or these are tickets. 3 reds. 2 of them are blue. They're going to be circular tickets, let's say, and 1 of them is yellow. Now, what's the chance of drawing 2 blues from the box with replacement? So you just take it one by one. What's the chance that the first one is blue out of 6 tickets? 2. Now you're sticking it back, so what's the chance the second one is blue? You still have 6 tickets, it's going to be what? It's with replacement, so how many? I take this one out and I stick it back in. So isn't it just 2 out of 6? Isn't that your answer? Yeah, and they're independent. All right, now let's just do exactly the same thing without replacement. The first one, the chance that the first one's a blue out of the 6 is 2, but now I don't put it back. So how many cards are left? How many tickets are left? 5. And how many of them are blue that are left? 1. Great, and that's dependent. All right, now what's the chance of drawing 2 tickets with replacement and getting at least 1 blue? All right, so right away you're going to think the probability of at least 1, that's going to be hard. Isn't it? So let's not do that. What do we want to do? We want to say the probability of at least 1 plus the probability of what? None is going to equal 1. Let's do this one. What's the probability of none? Well, we could, if you want to just remember, some people, we can solve it first this way. The probability of at least 1 equals 1 minus the probability of none. So now we say 1 minus, what's none? None. Out of the 6 cards, how many are not blue? 1, 2, 3, 4. So we got 4 of them that aren't blue. And it's with replacement, so let's say we got the yellow one. We're going to stick that yellow one back, and so it's just times 4 out of 6, right? Isn't that our answer? We can just leave it like that. Any questions on that? Now let's do exactly the same thing, but without replacement. So it's going to be what? If it's without replacement, it's going to be the probability of at least 1 blue is going to equal 1 minus the probability of no blues. Well, the first one's going to be the same. But now, let's say we got the yellow one. Doesn't matter which not blue we got. But we're not putting it back. So how many cards are left? How many tickets are left? How many tickets are left? 5 are left. And how many are not blue that are left? You only have 3. If I took this one, it doesn't matter which not blue I take. You assume it happened, and there's 1, 2, 3 that aren't blue. So does everybody see how that's your answer now? Does that make sense? Let's do the same thing with all and not all. Okay, what's the chance of getting all reds with replacement? All reds. We just start with the first. Out of the 6, how many are red? 3. And we'll just raise that to what power? Because it's with replacement to the 3rd. Now, what about not getting all reds? What's it going to be? Not getting all, remember, the probability of not all, that's hard, plus the probability of all reds, all 3, has to equal 1. Not all 3 would be hard. It means that we could get what? 0 reds? We could get all of these, or we could get maybe 1 not red and 2 of those reds, or 2 of these and 1. It's just so hard. So this is hard. So what are we going to say? The probability of not all, we're just going to stick that in there and solve it. The probability of not all is equal to 1 minus the probability of all, which is equal to 1 minus 3/6 to the 3rd. Is that good for everybody? All right, I think we're done with that. Now, we have another hard thing. We have another pretty complicated thing to do today. I wanted to give you time to do your homework, but I don't think I'm going to be able to, because I want to cover some more this conditional probability, and then we'll be done. All right, now, if you have a few conditions, more than one, if a situation involves 2 or more conditions, a table or a tree diagram is helpful. Otherwise, it gets really hard to keep everything straight in your head. So let's look at an example. All right, so suppose a box contains 30 aspirins and 70 Tylenols, and half the aspirins and 10% of the Tylenols are poisoned. All right, what's the chance of randomly drawing a pill from the box and getting poison? I think it's just really helpful first to fill out a table. You have 2 conditions, whether it's poison or not poison, and whether it's aspirin or Tylenol. So, and it doesn't really matter which you set up as rows and which you set up as columns. It's completely symmetrical, it doesn't matter at all. So, what do we know? Let's fill out this table. How many aspirins? What can we fill in just from looking at this? What you can fill in, where should I? The total number of aspirins goes right here, 30. We can fill that in. the total number of Tylenols. Where does that go? Total Tylenols right there. And so we can also fill in the total. So this is what we start with. We have that. And now what else can we fill in? We have to use all the information. Half the aspirins are poisoned. So what else can I fill in? Half the aspirins are poisoned. So what should go here? Half, right, half of 30. So that's 15, which leaves what? 15 here. Let's do the same. 10% of the Tylenols are poisoned. So we can say 10%, 0.10 of the Tylenols, which is what? 10% of 70 is 7. So how many does that leave? 63. Now can I fill in everything else from this? Yes. These are the totals. Total number of poisoned are 15 plus 7 is 22. And total number of not poisoned is 78. Now, check to make sure that 22 and 78 add up to 100, and they do. Everything checks out. Now we can answer the question much more easily. What's the chance of randomly drawing a pill from the box and getting poison? So we're drawing a pill. What should be in the denominator? 100, because you're looking at all the pills. Out of all 100, what's the chance of getting a poison? 22, all the poison. So that's pretty straightforward. Now, this is where people sometimes get confused. If someone randomly draws an aspirin, there's a 50% chance it's poison, right? Let's say you drew an aspirin out of there, and you see it's an aspirin, and you say, there's a 50-50 chance that it's poison. So some people think, oh, that must mean the opposite. Does it mean that if someone randomly drew a poison, that there's a 50% chance it's aspirin? It might sound logical, but let's figure it out, okay? What is the chance that it's aspirin if you know it's poison? Given that it's poison means you draw it, you know it's poison. So you already start, you know it's poison. So how many poisoned ones are there? How many poisoned? 22. So out of those 22, what's the chance that it's an aspirin? 15. Are those the same? Is that 50%? No. So don't be fooled by just, things in language. It's so much easier to lie with language than it is with statistics. It really is. I mean, you can lie with both of them. People say you always lie with statistics, but boy, you can just smooth talk somebody so much easier with language. Okay. Now let's look at this one. Suppose jurors make the right decision about guilt and innocence 95% of the time. All right, let's say that, you know they're not always right. Do you think the jury always gets it right? No. But let's say they got it right 95% of the time. All right? And suppose that 80% of all defendants are really guilty. I'm just making this up, this 80%. Maybe it's 20%, maybe it's 30%. I'm just saying, pretend it was 80%. All right. Now, what's the chance that somebody who's convicted is really innocent? And what's the chance of an acquitted defendant truly being guilty? So you probably, when you looked at this, you'd think, if they're right 95% of the time, then 5% of the time they're going to put an innocent person in jail, right? Isn't that what you'd think? And that, but is that really going to happen? Is that true? Given that if you have 80% are truly, let's think about it. I mean, let's not be so quick to answer this yet. So let's fill out the table. All right? So let's say I should give you a total. Let's say we start with 100 people, okay? Let's say we started with 100 people. Now, and you can pick any total, 100's a nice round number. Now, what can you fill in next? What do we know? Can we fill in any of these next? Look up here. What would you fill in next? Is there anything we can fill in? If there's 100 people, can we fill in any of these totals here? Any suggestions? Out of 100 people, from this information, is there anything I can fill in? Guilty. How many? 80. good. 80% are guilty. So we can, does everybody see that? That's the only thing that we can really do right now. So we're going to fill that in. Does everybody get that? Fill that in first. Right here. So that means 80. Now what can you fill in? It has to add up to 100. So how many are innocent? 20. So now we've got this filled in. All right. The only other piece of information is this right here. We've got to use that somehow to fill in. So let's think about it. It says 95% of the time they make the right decision. 95% of the time they make the right decision. All right. What's the right decision if somebody's innocent? Is it to put them in jail or to let them go? If they're innocent, what's the right decision? To let them go, to acquit. So here's the right decision, is right here, the right decision. This is right. If they're innocent, it's right. So 95% of the time they're right. So do you see how I should say 95% of those 20 are going to be acquitted, which means 19 of them. So we know that. If they really operated that way, if they were right 95% of the time, they'd acquit 19, and how many would they wrongly put in jail, wrongly convict? 1. So we've got that. Now, what if somebody's guilty? What's the right decision there? If you're on a jury and you make the person really did it, they're guilty, the right decision is then to what? Convict. So we want 95% of the 80 to be, if they did that, then 95% of the 80, which is 76, would really be convicted, which leaves how many of these guilty people would get off? 4. Great. Okay, so now we can fill in the rest of the chart. 19 plus 4 is 23 are acquitted, and how many are convicted? 77, and it adds up. We're good. All right, now we look at it and we can answer these questions. What's the chance of a convicted defendant truly being innocent? So what's the chance of all the people in jail or all the ones who are convicted? How many of those people are innocent? Yeah, right. You got this right away. So where are we, but help people out. What's this? So what are we putting in the denominator? What's the chance of a convicted defendant? You look at all the ones who are convicted. Wait a minute, maybe we didn't get it right. What's the chance of a convicted? How are we going to do this? How many people are in jail? How many people are really convicted? 77. Of those, how many are really innocent? 1. Okay, which is about 1.3%. Now, what's the chance of an acquitted defendant truly being guilty? So you look at all the people who are acquitted. Who are all the people who were let go? How many of them were there? There were 23 of them that were really let go. That's this right here. It goes in the denominator. And now how many of them were really guilty? 4. Okay, so you've got that. That's great. Let's do this last one. All right, this last one is okay, so this is these diagnostic medical tests always have these 2 conditions for whatever it's a test for. Here's a test for AIDS. This is actually the ELISA test was the most widely used test for years, and it was a 99% chance that if you really had AIDS, you'd get a positive test. So what were the conditions? You either have AIDS or you don't, and you either get a positive or a negative. And let's read what it says up here. It says, this was a very good test for AIDS, 99% chance that if you had AIDS, you'd correctly get a positive test. But so also, there's a 6% chance that if you don't have AIDS, you'll incorrectly get a positive result. You know, it'll be a false positive. All right, so now, and then, not very many people have AIDS. Only about 1% of the blood samples that were tested had AIDS. All right, so what's the chance that someone has the AIDS virus given that they tested positive? Let's think about this intuitively. All right, So pretend all of us, we're part of this population, that we're giving blood, all right? And somebody came back with a positive result. You don't know anything about their risk factors for having AIDS. What would you tell that person? Would you say, it's 99% chance that if they really have AIDS, they're going to get a positive result. And there's also a 6% chance if they don't have AIDS, they'll also get a positive result. So do you think that the person's going to be, what would you tell that person? Raise your hand if you think there's about a 90% more chance that he has. If you get a positive result, there's at least a 90% chance that he has AIDS. Raise your hand if you think that's true. Raise your hand if you think it's at least over 50% the person has. You get a positive result. Do you think it's at least over 50% the person has AIDS? Raise your hand. Raise your hand if you think it's quite unlikely the person has AIDS if they get a positive result. No one raised their hand for that. Okay, let's think about it. All right, pretend there's a lot more than 100 people here. Middle section, about 100 people. Pretend all of us in this middle section have gotten this test, all right? So let's write this down. Suppose that we have 100 people, okay? Before we even fill out this chart, because I'm not sure we have enough time. So suppose you have 100 people. All right, us. How many of us really have the AIDS virus if we were a typical population? Do any of us? One. Why? Because the 1%. So, all right, so who has AIDS? I mean, wait a minute. Sorry. Do any of us want to volunteer and say that we have AIDS?
No, ma'am.
No, ma'am. Okay, I'll be the one. I've been, I have AIDS. Haven't shared, just keep it amongst yourselves, please. Don't let this out. I'm just going to share this. Yes, I had a hard, anyway, I'm doing well. Taking my meds, so I have AIDS. You can write that down. One of us has AIDS. All right. Ooh. See, it makes me do weird things sometimes. Oh, you've got to be kind to me. Okay, so one has AIDS. One truly has AIDS, all right? Don't let it out, though. So, am I going to test positive, do you think? Yes, because why? 99% of the time, it's a positive result. So I'm going to get this positive result. I got the positive. Okay, so the one person tests positive. Now, how many don't have AIDS? Out of the 100 people?
99.
You're all clear. 99 don't have AIDS. Now, are any of you going to get a positive result?
Yes.
Yes. Great. 6 will get a positive. Where are you reading that from? 6% chance. That's where he's getting it from. 6% chance he'll get a positive. So 6 will get what's called a false positive. Now, all right, 6 will get a false positive. Now let's answer this question. What's the chance if someone has AIDS given the person tests positive? How many tested positive altogether out of these people? 7. And how many really have AIDS? 1. So that is the chance, which is only about a 14% chance. See, surprise you, not one person in here thought the chance was less than 50%. So this is really important because this type of thing happens all the time. It actually happened to me, not with an AIDS test, but with another type of test where the doctors don't understand this. Any of you who are going into the healthcare field, and a lot of you are, I want to educate people because, basically a test like this was given to doctors and only 15% of them got it right. So now if we filled in the chart, because that's what you're going to have to do in your homework, let me fill in the chart and we can see that we'll get the same thing. All right? So if we filled it in for 100 people, 1 would have AIDS, 99 wouldn't. Now, out of the 100, whoa, this is out of the 1. We'd have a 99% chance. Let's be more, instead of saying 0.99, I'm going to give you some more zeros here so we can get whole numbers. All right? How many, let's see, if I gave you 2 more zeros. Okay, so let's just add 2 more zeros to everything. It's the same thing. 1% of 10,000 is 100. All right, so now we're in this situation. 1% of the 10,000 people have AIDS, 9,900 don't. All right, that's 99%. Now, if we look at this, how many of the ones who have AIDS are going to test positive? How many? 99%. So 0.99 out of the 100, so what is that? 99. How many will test negative? 1. Now, if you don't have AIDS, how many are still going to test positive? 6% of the 9,900. And so that is, I'm just doing a little more exactly than what we did here. And that is 594 is 6%. So 594 plus what? 9,306. That has to add up to that. All right, and so now we can do the totals, 9,307, and we can add these together and we get 693. And these add up to, okay, we're good. So now if we did the same problem, not intuitively, but just from the chart, how many test positive? If we did it from here, what are we doing? How many test positive? 693. And how many truly have AIDS? 99. And that's approximately equal to 1/7. It's almost the same thing. All right? Now, what's the chance that someone has the AIDS virus given they tested negative? Let's say they tested negative. How many people tested negative? How many people tested negative total? And how many really have AIDS? 1. This is tiny. That's why the test is done this way. This is tiny. You can always get retested. You know, if you test positive, you go in and you get retested. But what we don't want, this is why we want this chance to be really, really small, because we don't want an infected person to be given blood. Okay, that's it for today.